So, welcome to lecture series on advanced linear algebra. We have seen when a linear operator is defined over a finite dimensional vector space, where the vector space is having direct sum decomposition of some subspaces which are invariant under T, then the operator having direct sum decomposition of some finite operators which are basically restriction of the operator T to corresponding subspaces. Now, question is, if one consider a general linear operator on a finite dimensional vector space V, then what we can say about this operator? Whether is it possible to have a direct sum decomposition of the space V under some subspaces, and the operator can be decomposed as a direct sums of some other operators which are basically restriction to the operator, the original operator T to the corresponding subspaces. Let me quickly write down the questions so that we can see the importance of these questions and how to answer the question, please. So, what I am saying that let T be a linear operator on a finite dimensional vector space capital V over the field capital F. Question is, does there exist a direct sum decomposition of vector space V, that is, does there exist subspaces like W1, W2, Wk, so that V can be written as something like W1, W2 to Wk, and the operator T can be written as something like T1 plus T2 plus Tk. So, this is basically the question, please. So, does there exist a direct sum decomposition of V like this, and the operator T can be written as T1 plus T2 plus Tk? I mean, does there exist such type of operators, linear operators, which are basically restriction of T to the corresponding subspaces, please. As earlier we have seen, when the vector space is having direct sum decomposition of some invariant subspaces. So, in that case we have seen that T can be written as sum of some operators like T1, T2, Tk. Now, to answer these questions, if I look in terms of the eigenvalue and eigenvector of the operators, so we see that there are two problems. The first problem is what? The operator T may not have eigenvalues. Over the given field. So, that is basically the drawback of the field. But this drawback can be overcome if we change this field to a field which is algebraically closed. So, in that case this problem will be resolved. However, second problem is T may not have sufficient eigenvectors to act as a basis of the space B. So, for example, if I consider say capital A equal to, let me consider 3 by 3 matrix 2 0 0 1 2 so this matrix. This is a triangular matrix. So, certainly eigenvalues are 2, 2 and minus 1. Eigenvalues are 2, 2 minus 1. So, x minus 2 whole square into x plus 1 is the characteristic polynomial of this matrix space. We see eigenvector associated to eigenvalue, I am just considering the lambda equal to minus 1. Then I will have A minus lambda I. If I consider this matrix, I will have this matrix and this operating on x equal to 0, that will give the basically eigenvectors associated to eigenvalue lambda please. So, this implies that I will get your A equal to okay. So, I will have so, I will have basically A minus lambda I multiplied to x equal to 0 implies this matrix space. So, this implies I will have x1 equal 3x1 equal to 0. So, it implies x1 equal to 0 and x1 plus 3x2 equal to 0, since x1 0 means x2 also equal to 0. So, this implies E3 is equal to 0 0 1 is the eigenvector associated to lambda equal to minus 1. Now, similarly, if I consider eigenvector associated to eigenvalue equal to plus 2, I will have what? I will have basically 0 0 0 1 0 0 and I will have 0 0 minus 3 into x1 x2 x3 equal to your 0 0 0. So, this implies that I will have x1 equal to 0 x3 equal to 0 implies E2 which is equal to 0 1 0 is the eigenvector associated to eigenvalue equal to 2, and I will have only one eigenvector associated to eigenvalue lambda equal to 2, because this matrix is having rank equal to 2. So, the nullity equal to 1. So, I will have like this. But interestingly, you see if I consider say here A minus 2 I equal to I have 0 0 0 1 0 0 0 0 minus 3. Now, if I consider A minus 2 I whole square, then I am getting what? I will get basically just use your normal calculation, you will have like something like this, you can check it, A minus 2 I whole square equal to this. So, null space of A minus 2I whole square will be what? That will basically A minus 2I whole square operating on x equal to 0, that we have to solve it. So, this means that then I will have x 3 equal to 0. So, I will have E 1 equal to 1 0 0 and E 2 equal to 0 1 0 as two linearly independent solutions of A minus 2I whole square operating on x equal to 0 case please. So, the dimension of the null space of 2A minus 2I whole square is 2. I will have two linear independent vector please. Now, you see the beauty here. So, null space of A plus I, which is spanned by E 3. So, that is, let us consider, let be W 1, and null space of A minus 2I whole square is spanned by E 1 and E 2, let it be called as say W 2. Then we see that the vector space V is equal to direct sum of W 1 and W 2. So, when I consider the null space of A minus 2I whole square, rather talking about the null space of A minus 2I, then I am getting the vectors, linearly independent vectors in the null space, and then we are able to have a direct sum decomposition of the space V in terms of W 1 and W 2 please. So, this give a hint to think about the whether if I consider any linear operator defined over a finite dimensional vector space, whether it is possible to have direct sum decomposition of the space as well as operators. So, this is basically we will answer these questions in terms of using a more general theorems called primary decomposition theorem please. So, the primary decomposition theorem will tell us when a linear operator defined over a finite dimensional vector space, then using that theorem we will be able to say that the operator can be written as a direct sum of finite linear operators, and this space also can be written as direct sum decomposition of invariant subspaces. So, let us talk about the what is primary decomposition theorem please. Primary see, in my previous example what I have considered when the characteristic polynomial is factorizable over the space, but this primary decomposition theorems does not require whether characteristic polynomial will be factorizable or not. So, it is more general way to prove the existence of direct sum decomposition of the space as well as operator please. So, what is that? It is like this, let T be a linear operator on a finite dimensional vector space over the field say capital F. Let P be the minimal polynomial of T, and P equal to something like P1 power R1 into P2 power R2 into Pk power Rk, where Pi are monic irreducible polynomial over the field capital F, and Ri are positive integers. Let W1, W2, Wk be the null space of P1 power R1 operating on T, P1 R1 T, P2 R2 T and Pk Rk T, please. Then first V is direct sum of W1, W2 plus Wk. So, V will have direct sum decomposition of the subspaces W1, W2, Wk. Second, each Wi is invariant under T. Third, if Ti denote the restriction of T on Wi, then the minimal polynomial of Ti is Pi Ri. So, this is the theorems. He is saying that if a linear operator defined over a finite dimensional vector space V, where the space is defined over the field capital F, if the minimal polynomial of the operator is product of P1 power R1 into P2 power R2 into Pk power Rk, where Pi are monic irreducible polynomial over the field capital F, and if W1, W2, Wk are the null space of the operator P1 power R1 of T, P2 R2 of T2, then V will be direct sum of W1 to Wk and each Wi will be invariant under T, and if Ti denote the restriction of T on Wi, then minimal polynomial of Ti is Pi power Ri, please. Okay, suppose this theorem is proved. Now, what we will get from these theorems? Now, this theorem will basically tell us a nice structure of the operators. So, let me consider the situations when monic irreducible polynomial P1, P2, Pk are basically first degree linear factors. So, when P1 equal to suppose something like x minus C1 and P2 equal to x minus C2 and so on, Pk equal to x minus Ck, I mean to say when the field is algebraically closed, under that situations I can write down that each monic irreducible polynomial as a product of linear factors. So, in that situation what I am getting, minimal polynomial will be, it is of the form of x minus c1 power r1 into x minus c2 power r2 and x minus ck power rk, where c1, c2 and ck are distinct eigenvalues of the operator T. Then if you define D is operator like C1 into E1 plus C2 into E2 plus CK EK, where E1, E2, EK are projection operators. Actually we will see it here, this V is direct sum of W1, W, Wk. So, our previous result says that there will be projection operator on W1, W2, Wk. I mean, in that case the identity operator can be written as E1 plus E2 plus Ek. So, using this same concept I am writing here, this Ei is basically that projection operator. So, if I define another operator D as C1 E1 plus C2 E2 plus Ck Ek, then using that theorem D will be a diagonalizable operator. So, if I can write that D equal to C1 E1 plus C2 E2 plus Ck Ek, then certainly D will be a diagonalizable operator. We will say D is diagonal part of the operator T. So, let me define n is another operator is defined by say T minus D. So, if I take out the diagonal part of the operator T, that I am saying that say n, then we have T will be equal to how much? T will be T E1 plus T E2 plus T Ek and D equal to C1 E1 plus Ck Ek So, this implies T minus D will be equal to T minus C1 I into E1 plus T minus Ck I into Ek. So, this implies the new operator n, which I am defining as T minus D, equal to T minus is something T minus Ci I into Ei, I equal to 1 to say k. So, this implies if I consider n square, you will see that it will be equal to sigma T minus Ci I the whole square into Ei, I equal to 1 to k. So, in general n to the power r also will have I equal to 1 to k T minus Ci to I power r into this one. So, see Wi is what? Wi is basically according to primary decomposition theorems, Wi is the basically range of projection operator Ti. So, this means that n to the power r equal to this. So, for r greater than Ri, I equal to 1 to k, n to the power r has to be 0. Since each t minus C I power r is 0 on the range of E I. So, this means this n is called as a nilpotent operator, n is called as a nilpotent operator. What is nilpotent operator? A linear operator n defined over a vector space V is called nilpotent operator provided there exists a positive integer n such that n to the power n equal to 0, but n to the power n minus 1 not equal to 0. So, using primary decomposition theorems, when a linear operator T having minimal polynomial as the product of linear factors, in that case we have say n equal to, I have written n equal to t minus d. So, this implies t equal to n plus d. So, the operator t as a sum of the nilpotent operator and a diagonalizable operator. So, this is the beauty of this theorem please. So, one can split the operator T into sum of one diagonal operators and nilpotent operators. Now, this spectrum, this T can be written as n plus d will certainly help to have a simplified structure of the operator. So, we see that using primary decomposition theorems, when we apply this theorem to a linear operator whose minimal polynomial or whose characteristic polynomial is product of linear factors, in that case the one can have a nilpotent operator n and a diagonalizable operator d such that the T can be written as d plus n as the sum of nilpotent operator and diagonalizable operator. Now, this concept will help us to have a simplified structure of the operator please. So, we will discuss more about all this issue and also the proof of the primary decomposition theorems, which I have not done it. I simply use these results, but we will see the proof in next class please.